Hello friends, welcome to my channel. Let's have a look at problem 2368, Reachable Nodes with Restrictions. So in this problem, we're going to share some solutions based on traversal. So either breadth first search or depth first search. So the problem is the following. So there is an undirected tree with n nodes labeled from 0 to n-1 and n-1 edges. So because we have n nodes, because this is a tree, so there are n-1 edges. We are given a 2D integer array called edges of length n-1, where edges I equals ai bi, indicates that there is an edge between nodes ai and bi in the tree. We are also given an integer array restricted, which represents restricted nodes. So we are required to return the maximum number of nodes we can reach from node 0 without visiting a restricted node. So here, note that the node 0 will not be a restricted node. So this is a consistency assumption, right? So here are two examples. So let's look at example 1. So in example 1, so the nodes 4 and 5 are restricted nodes. So starting from the root or the 0 node, we can visit 1, 2, 3. So the output is 4. So in example 2, so we can visit 0, 5, and 6. So 3 is not reachable. So in this case, we have 3 nodes. So we return 3. So let's also look at the constraints. So first, so the number of nodes can be up to 10 to the power 5, which is a decent large number. And also all the values of the restricted are unique. So actually we can interpret this restricted as a set. So with that said, let's look at the method we are going to present. So the method is standard graph traversal. So we can use breadth first search or depth first search. So basically the breadth first search or depth first search, if we want to write iterative format of codes, so it depends on the container. So if we are going to use breadth first search, then we are going to use a queue as a helper. So if we want to write depth first solution, so we are going to use stack as a helper. So with that said, so our coding plan is the following. So first we are going to build the graph, and then we do a traversal helper function, and finally we return the count. So in between, we're going to explain the code line by line. So with that said, let's look at the code. First, let's do this first step, build the graph. So notice that this graph is undirected, or put it another way, it's a bidirectional edge. So notice that tree is a special kind of graph. So let's first build the graph. I'll call this graph. So basically I'm going to use a list and neighbor representation. So default dict. So I'm going to use a set as a container. So this is actually this dictionary. So use the nodes as a key and use their neighbors as the values, right? So with that said, let's traverse the edges for AB in edges. Then we're going to do this. Graph A, notice that graph A is a set, so we want to add this node B. And also we're going to use B and A due to the bidirectional nature or undirected nature. So with that said, we finished the build of the graph. And the second step is to do a traversal helper function. So here I'm going to use a depth first search just for convenience. So here the restricted, as the problem stated, so those are the nodes we cannot reach, right? So actually we can initialize a visited site to be set restricted. So this visited will play two roles. First, it encodes the information from the restricted, right? So and the second, it will add a checker for us to avoid repetition in our traversal. And next, with this done, we're going to do the depth first search. So, or if you like, you can call this traversal function. So we are going to have a source, so which is a node. We are going to do depth first search from node 0. And then we want to count the number of nodes we can visit. In other words, we want to count the size of the connected component starting from the source. So we're going to initialize a count variable, initially 0. And then to do the depth first search, we're going to use a stack, and we put the source here. And then we're going to do the iteration. So while stack. Then first we're going to get the node. So the node is stack pop. So we are popping from the tail of the list of the array corresponding to the top of the stack. So then once we pop a node, we're going to increment the count by 1. And next, we also need to add the current node to the visit site so that we do not visit it a second time. Then with that done, so we are ready to look at the neighbor of this node. So for neighbor in graph node, then we just need to check if neighbor not in visited, right? So if it's not in visit, we're going to append it to the stack. So that's it for this traversal process. Then here, let's return count. So this is the hyperfunction we're going to use. And the third step is return the result. So for this, because the DFS will return the count directly, then we can do return and DFS, the source will be 0. So that's a full code for this specific problem. So let's look at a special case check. Yeah, it passes the first example, I guess. Now let's do a generic case check. Yeah, it passes all the cases. So now, if here we are using pop from the tail, so this is a depth first search. So if we pop from the very left, this corresponds to a breadth first search. So you can try to test that. Yeah, it also passes all the cases. So notice that you can also write this solution or the hyperfunction in a recursion format. So that's actually also good to try. So with that said, I guess that's about it for this problem and this video. You are welcome to follow up other videos in my playlist or in my channel. Thank you very much.